for the early universe.
Okay.
Reconstruction problem.
Thanks a lot. So, yeah. You know how it works? Yeah, you are so gifted, so just for the light. Or maybe there is a stick.
No.
Yeah. Ah, yeah, there is a stick. I prefer the stick. Yeah. Yeah, very good. Okay. Okay, I will use the stick instead. Okay, so thanks a lot for the invitation to be here. And so in this talk, I would like to start by describing the model for this early universe problem, which is a modification of the Newtonian gravitation. And after that, I will discuss the so-called Zeldovich approximation and the way we can understand that using the Monge-Ampère equation. Then there will be some discussion about the least action principle, and the gradient flow solution will come up, and eventually I will describe a numerical method, at least in the 1D case. So that's the outline. Okay, so these problems is for interest in cosmology. So I think this was started by Peebles, and I know this problem from Uriel Frisch for Observatoire de Nice. And so most of the physical background I know is due to Uriel Frisch. And the attempt of these people is to reconstruct the history of the universe, so it's very pretentious, from the knowledge of the present distribution of matter in the universe. So you have the picture of what you see from the observation, and you want to guess what could be the evolution of the sky in the past. So this picture is taken from an n-body simulation, and you see that, and this is vaguely, I mean, it's quite similar to what you can observe, and you see that one of the main features of the universe, if you observe it, is that the matter is highly concentrated. So you see the yellow spots are like point concentration, but you see some kind of filaments on walls where the matter is concentrated on maybe a set of larger dimension, but not, in some sense, nowhere. It's everywhere concentrated, in some sense. And so we want to unreveal the history beyond that. So what is the model they use? So they don't use a full Einstein equation as they should do. So what they do, they typically take the exact solution for an expanding universe, so like this Big Bang style. So technically this is an Einstein de Sitter universe, and they consider that in a perturbative way that the matter is evolving according to the Newtonian law in this background. So the general relativity provides the background, and the matter is evolving according to Newtonian law. And you get the following equation. So let me denote, you take like a particle. So here the particles are very big, because in a simulation typically the particle is maybe like, how many? Like 100,000 or million years light long. So it's very big. So it's not even galaxies, it's cluster of galaxies or particles. So there is, in this framework, this is not this is a special time. This is some co-moving time. And so A is the label of the particles, and capital X is a position in the three-dimensional space. And this is the equation they use. So you see, this is pretty much like the Newtonian gravitation, except the red terms. So you get the acceleration of the particles, and this is balanced by the gravitation potential, and the potential is computed as for the Newtonian law. So rho denotes the density of the particles. So this is just the integral with respect to the label of the location of the particle. So this is the definition of the density field. And you have a Poisson equation. So this is a nabla. Nabla phi is balancing the difference between rho and the average. So 1 is a kind of average of the density. And so everything is Newtonian except the red terms. So everything which is in red comes from general relativity, this Einstein de Sitter background universe. So you have this term, this t in factor of the second order derivative. You have the dx dt term, which is of course not in classical Newtonian gravitation, and you have a t here. So the only input of Einstein theory is here, there, and there. Otherwise, it's completely Newtonian. And so the quite funny observation is that when t approaches 0, you know the velocity takes over on the acceleration. So at very early time, the dynamics is first order, not second order, which is amusing. And as I like to say, I mean, this means that if you correct Newton by Einstein, you go back to the mechanics of the Greek, where it was believed that the force was balancing the velocity and not the acceleration, which corresponds to any motion dominated by friction, right? And so now it's coming back through biology, because in biology, of course, everything is first order mostly. Acceleration is negligible. So that's an interesting model, and even more surprising, you have these initial constraints. So I wrote again the equation, and you see that at time 0, you have very severe constraints on the model. So first of all, I mean, if you want things to be reasonably bounded, you must have the density to be 1. Okay? So the density is uniformly 1. So, and also at time 0, you see that the velocity is slaved by the gravitational field. So there is no option. So you cannot prescribe the velocity field freely. So actually the matter looks like a continuum medium, uniform at time 0, with a monokinetic velocity distribution. So you see that at this level we are very far from the classical gravitation description. And so let me write this. So let me write, so the density is 1 at time 0. So I will, so I can take the label of the particle to be the initial position. So x0 can be seen as the identity map. And the initial velocity is balanced by the initial gravitational field. And you see that there is singularity also in the Poisson equation, because Laplacian of phi is equal to rho minus 1 divided by t. And rho is 1 at time 0. So the only thing you can do is to prescribe the grad phi 0 is related to the time derivative of rho at time 0. So I will do that in the next slide. But I mean, with this model, as a logical consequence of this model, there is no discrete particle at time 0. You know, it's like a continuous medium. So if you want particle later, it means that you need a concentration mechanism. So the granularity of the matter must come from a concentration mechanism. It's not at the origin in this model. So which is also completely different from the classical Newtonian view on gravitation. Okay, so you see also that in this model the only possible initial condition you can give to the model is this fluctuation of density. So that is the limit of rho minus 1 divided by t at t equal to 0. And this is these things which is balancing the gravitational field at time 0. So to get and so once you get the gravitational field at time 0, you get the initial velocity field, like here. And so there is no other possible data. So if you compare with a classical Vlasov-Poisson system, which would be the canonical way of describing Newtonian gravitation, it's completely different, because not only there is no distribution of velocity, but there is only this scalar initial condition. This is the only initial condition, it's scalar field. So if you compare with Vlasov-Poisson, for Vlasov-Poisson, the initial condition should be a phase-space distribution of velocity at each point. So it's a much, much richer initial condition. So there is a very strong limitation with this. And so this makes plausible the EUR problem, so early universe reconstruction. And this, for instance, you can look at the paper of Frisch in Nature. So this is the idea that you might be able to reconstruct the history of the universe from the only observation of the present density field, rho at time capital T. Because you are observing one scalar quantity, then therefore it makes sense to be able to reconstruct this scalar field, which is enough in some sense to start the evolution. So for instance, for the Vlasov, for the classical gravitation, this would be irrelevant because you cannot expect from the only density field to recover the full initial condition. So that's the idea of these people. Okay, and so I said the only initial condition to recover, and this is the density fluctuations field, and this is where this problem is interacting with high energy physics, because the modeling of this initial fluctuation field is a matter of quantum mechanics in some sense. So this is supposed to be a random field, and for instance, well, think about the case where we would have only one space variable. So this would typically assume that this is like a white noise. So this means that the initial velocity will be like a Brownian curve. The initial velocity profile would be a Brownian curve. This is why people studied this model with Brownian initial condition for the velocity. Okay, so, but of course, one of the big problems is to take into account the phenomenon of dynamical concentration for the reconstruction process, because we expect this field rho T to be highly concentrated. So it is not supposed to be a smooth field, because it should be completely granular, right? Because of the effect of concentration. And so this makes the problem more difficult. Okay. So now, okay, this is once again this picture of the resulting from n-body simulation with this kind of model, where you see that the result is very concentrated. And now let me tell you about the so-called Zeldovich approximation. So in the 70s or late 60s, Zeldovich suggested a formula to approximate the solution of this model. And the formula is so ridiculously simple that it's a little bit shameful to explain. Well, he suggested that, you know, to leading order, the particles just move along rays, straight line. So, and the initial velocity, of course, as it should be, is given by the gravitational potential through the, so this is a typo. I mean, this should be rho 0 prime. What I call here 0 dt means stands for rho prime 0. I forgot to change that. Okay, and so it turned out that, well, I mean, you could think, well, this is a stupid type of approximation, like first order Euler explicit scheme, but actually it turns out that in 1D, for instance, this formula is correct. So there is a nice compensation. So you see that this formula, the acceleration is 0, so this cancels this term. But also by looking more carefully at the formula, it turns out that this is the velocity is exactly balanced by the gravitational potential in 1D, due to this elliptic equation. So this formula is, I mean, the first time I saw that, it looked like a joke, but actually it's a pretty good formula, and this is really interesting because this is the output of mixing the Newtonian gravitation with a bit of Einstein equation, and then you get the motion along straight line. So this is a bit strange. Okay, and so, okay, let me make this joke because this was reminiscent of this, I think maybe not so many people are knowledgeable in Latin any longer, right? But so this is taken from this De Rerum Natura from Lucretius. And so it is not completely related to my talk, but I think it's very much related to kinetic theory, because in English, you know, this is the Klineman theory. And that's quite interesting to read, actually. You know? So everything moves along straight lines, but you have a little bit of deflection. So in my case, this would be more like the initial condition, because this is also possible in time, according to Lucretius. So you can move straight lines, and from time to time you move a little bit. And this is the way that things, I mean, the reality comes from that, right? Because of the collisions. So I think it's nice, right? Because this was written a long time ago, right? So I think that the translation is more or less accurate. So maybe let's check that collision is really there. I'm not so sure. I don't see collision, strictly speaking, but well, anyway. You see, no? Okay. So François, maybe you can help us. Okay, so this is a plot of a numerical simulation of the model for corresponding to this Zeldovich solution. I will go back to this picture later. So I don't really tell you exactly the way it has been computed, but anyway, you should keep in mind the two important things, that the trajectory. So this is the time axis, and this is the position axis. So the first thing that you see, straight lines, and the possibility of collision. So this is like a sticky collision, very dissipative one. And so you see the mechanism. And so this is like a caricature of the previous observation, that by mixing motion along straight lines and collision, you can produce density distribution that are much more concentrated than before. For instance, here there is only one delta at the final time. So this is the basic mathematics. So now, in order to make an analysis of that, well, let me use the following observation. It turns out that this Zeldovich formula, which is exact in 1D, would be exact in any dimension if we would cheat with the model. Okay, and cheating with the model amounts to substitute this nonlinear equation for the linear Poisson equation. So instead of considering that rho is 1 plus t times the Laplacian of phi, we consider that rho is the determinant of the identity matrix plus t times the Hessian matrix of the potential. Okay, so this is a little bit of algebra, but if you do that, if you change the model, it turns out that the Zeldovich solutions are a solution of the model. So you could say, if you like the Zeldovich approximation, you could say that instead of considering them as approximate solution of the original Poisson model, let us consider the Monge-Ampère model as an approximation of the Poisson model, and in which case the Zeldovich solutions are exact. Okay. So now the thing that should be done is to check how far we are if we consider that anyway all these equations are simplified version of the Einstein equation, which involves some curvature terms. So I must confess that I didn't do it, but I think it would be nice to compare. And also you see that the time is helping, because when t goes to 0, you expand the determinants. So the first term is 1, and the next term is the t times the trace of the Hessian. But the trace of the Hessian is exactly the Laplacian. So this is linearly correct. So of course you make mistake in higher dimension for the next term. In t squared and t cubed, there are some extra terms when you expand the determinant. So by doing that, we are neglecting some second order terms in time. Okay, so but anyway, the interesting idea with the Monge-Ampère equation is that you can do, as we are going to say, we can deal with the concentration phenomenon in a more satisfactory way, I would say. You know, I mean, the people who have, I mean, there are many people here working on chemotaxis type of equation, and you know that because of the Poisson equation, you have a lot of troubles when the density concentrates. So there are a lot of work in the recent years about this idea, but the good thing about using the Monge-Ampère equation is, in some sense, you don't care so much about the concentration of measure. It is well suited to that. Okay, so this is the model I'm going to consider. And if you don't like the idea of modifying the model, you can consider that I'm just working in 1D. You see? So to be on the low key side, just consider that I'm just working in 1D. Okay. Okay, so now I need, so this is maybe the most abstract slide. I need really to see that in a slightly more geometrical way. And for that, I need a little bit of abstract nonsense. So D will be my domain. So the domain of the A. So typically for the early universe problem, I mean, as a simplification, people would take the, for instance, the torus, the periodic box. So you can imagine that D is a periodic box. Okay. And now in this, so I consider the Hilbert space of L2 map from the domain into RD. Okay. Bon. And in this Hilbert space, I will distinguish a subset which is made of, so this is the most abstract, I think, thing, which is made of all maps which go from D to D and are volume preserving. So a nice way to express this property is to say that whenever I integrate a function f which is continuous, I assume that D is bounded. So the integral of f composed with s should be the same as the integral of f. So this is just the action of s on this kind of integral is the same as the identity map. So this is a set of Lebesgue measure preserving maps. I mean, if S is a diffeomorphism, this just means that the Jacobian determinant of S is 1. If it's an orientation preserving diffeomorphism, then this S is made of all the orientation preserving diffeomorphism of D that have a Jacobian determinant equal to 1. And so this as and so now I can define in an abstract way the Monge-Ampère gravitation. So this is, of course, I will not provide a proof of the calculation, but it turns out that you can encode the Monge-Ampère gravitation model by a list action principle. And so you define for any curve depending on time in this Hilbert space. So it's a time-dependent map. And you build up the action in this way. So there is a kinetic energy part, which is just the velocity. So this double bar stands for the L2 norm. So x is infinite dimensional, right? So you have that. So this is a scaling factor due to this Einstein-de Sitter universe. So you need that. And now what is the potential part? It is, well, I mean, this is minus the potential because this is an action. This is not an energy. This is the action. And so the potential is given by, it's a little bit of Ginzburg-Landau type. So it's a kind of discrepancy. It's the square of the distance function from X to this set. You know? So if you are located on this set of volume preserving map, you don't pay anything. But if you are not, you have to pay this square distance to the set. And this is multiplied by t to the minus 1/2, again, because of this Einstein-de Sitter background space. So this is the action we have. So nicely enough, it's made of two positive terms. So it makes sense to consider the minimization of the action as a way to, for instance, to solve the early universe problem. So it's nice. I mean, if you, for instance, you know that in the case of Coulomb interaction, the action would have the opposite sign, for instance. Okay. So that's in this, for the action, I mean, the fact that you have a gravitational phenomenon is more or less helpful in some sense. Okay, so now this action has a very interesting structure, I believe. So you see, once again, this the potential part is made of this term, but this is a square distance function to an object. And so maybe it's good to draw some picture. So when you have an object like that, this is S. and you look at the distance function, so it could be like this. Okay, so the gradient, if you take a point, actually, if you want to compute the gradient of this distance function, this is related to the square distance between x, the distance between x and the projection of x on S, the closest point. And therefore, when you compute the gradient, you have this relationship. Actually, you know, maybe you know that from some other framework. You know that the distance function in image processing, for instance, has the property that is solution of the iconal equation. That is, the length of the gradient is 1. So here, the length of the gradient square is balanced by the function itself. So you have this relationship. So let me rewrite the Monge-Ampère gravitational action like this, where I put, instead of the potential, I substitute for the potential Q this gradient. So what's the point with this? The point is that now we have an action made of two squares, the sum of two squares. And this is advantageous because actually we can rewrite, the sum of these two squares as a single square. And why is it so? Because when we do the expansion integrating by part, we see that the difference between these two expressions just involves the boundary in time. So in the least action principle, you know, you fix the value of the function at t0 and t1, and you try to get critical points, minimal points. And therefore, any terms which depends only on the boundary data doesn't play any role. So between this expression and this one, there is nothing. This is like a null Lagrangian. So minimizing this or that, when you prescribe the value of x at t0 and t1, is the same, formally. But of course, now we have a nice feature of this action that we can find trivial minimizer of the action just by solving this first order equation. So we have a an action principle which of course would lead to a second order equation in time, but we wrote it as the square of a first order equation in some sense. So that's an interesting feature. And this is a trick actually which comes up in other fields, and this is like in Yang-Mills when you work with this BPS field or the instantons. This is the same kind of trick. So you reorganize the square and you find that you get trivial solution of the equation which have one order less of derivation. And so in some sense in this theory, the solution of this equation plays the role of the instanton in some sense. So any solution of this first order equation will be a minimizer of the action. And so that's clearly linked to the fact that the potential has this structural property that it's equal to its own square, gradient squared. Okay. And even better, it turns out that when you look at the equation, the Zeldovich solution are just the exact solution, at least for short time. I mean, I'm not talking about the solution in the global way. I will move to that in a moment. But at least for short time, these Zeldovich solutions are just exact solution to this first order equation. So this is a way to recover the fact that Zeldovich solutions are solution of the Monge-Ampère gravitation model, because they are obvious minimizer of the action. So it doesn't mean that all solutions are like this, because when you look at the formula, you see that if you know x at some time t0, then according to the, except maybe at time 0, but if you start at time t0 strictly positive, the knowledge of the solution of the equation, so you are not free to choose x t1. So this is why in the least action principle you may have solutions that are not like this, right? Because if you minimize that, you may have solutions that are not exactly cancelling the term, because the data of x at t1 and t0 are not compatible with the first order equation. But anyway, at least we get as special solution this solution of the first order equation. So now a good thing about this kind of equation, at least away from t equal to 0, where there is clearly a degeneracy, is that this type of equation can be seen as gradient flows. Okay, so up to this time, this time dependence of the model. So now let me do a little bit of calculation. So let me introduce this function r of x, which is a discrepancy between x squared and q. And if you play with the formula, you see that this can be written as the supremum of, this is the inner product in H, in L2, between x and s minus 1/2 of s squared for every people in the set capital S. And so this has a structure of a Legendre-Fenchel transform. It's a supremum of affine function of x, and therefore this is a convex function. And even better, because S is bounded, this is a Lipschitz convex function. So this new function R is a Lipschitz convex function in the Hilbert space. And so I need a little bit, just a little bit of convex analysis, a very light touch of convex analysis. So there is, well, if you know the theory, you really remember maybe the subdifferential, but let me skip that. So I mean, this is more seriously called, I call it lazy for fun, but this is called minimal section. For instance, I think this would be the terminology used by people like Ambrosio Savary. They would say the minimal section. So you take you fix x, and now you consider the w such that you have this inequality for all z in H. So this is a supporting plane for the convex function R. So you see, you can draw the. You have so when you have, for instance, a kink, convex function with a kink, you have many possible supporting plane. Oh, this is bad. Like this. And among them, you take the one that has the smallest norm. And this is uniquely defined. So this is a good thing. So this is a way of describing the gradient of a convex function when there are kinks. And the nice thing is if you use the the classical theory of maximal and monotone operator theory, you can solve the first order equation. Let me go back just a moment to this equation. You can solve at least away from t equal to 0, which is special, but you can solve this equation in the sense of maximal monotone operator theory, and we get unique global solution continuously depending on time valued in H. They are not differentiable, but they are right differentiable at any time. So, and this is important, the derivative can be discontinuous. You can have jump, but the right derivative is always balanced by the lazy gradient. So this is substituting for the gradient of Q, and then you input the lazy gradient of R, and this gives you the solution of this first order equation. Okay, and so now what is the idea? So okay, so maybe I should go back a little bit before. So now we have a least action principle, and we can, out of this action principle, we can get the set of equations with the Monge-Ampère gravitation. The problem is if you look at the equation, then the velocity cannot be discontinuous in time. And this is annoying because you cannot encode the collision of particles with the model of sticky particles, because when two particles stick, they conserve the momentum but not the energy. And for some reason, this is ideology. We want to favor the concentration phenomena by dissipating the energy. So if we stick with this the original formulation of the least action principle, there is a problem. But now, thanks to this first order theory, we know that in this first order theory, actually the velocity are not continuous in time. It's like, so the energy can be dissipated, and this is good for concentration. So now the idea is to modify the action principle in such a way that all solution of the gradient flow equation will be minimizer of the action. So which means that we have to modify the action in some sense, because the very earlier action principle would not allow this kind of discontinuity of the velocity. So in some sense, what we are doing is to get a least action principle where we can dissipate the energy, which seems to be a paradox, because usually, I mean, when you have an action principle, you have some reversibility in time. It seems to be completely impossible. But actually, thanks to this theory, we can do that, because the proposal is to use the modified action. And when you have concentration, this is not the same as before, where you input the lazy gradient of the convex component of the potential. So this is the proposal. This is a new formula. And you can check that, of course, as if there is no concentration, there is no difference between the previous action. So if you have a curve which is avoiding any concentration, then there will be no difference with the previous action. So without concentration, we don't change anything. But this way, we can have minimizer of the action that dissipates energy. So this is the least action principle with possibility of dissipation of energy. And so just for the complexity coordinate, this is the formula, and this is, well, it's manageable for the computation. For instance, in the 1D case, you can get explicit formula for this kind of thing. And for instance, maybe I skip that. Okay. So now, let me show you some numerics. So consistently, I did it in 1D. So I mean, you could consider this is for Poisson equation, because there is no difference between the Monge-Ampère model and the Poisson model in 1D. So that's fine. Here, I don't change the things. So what we do some experiments where we try to get the history of the motion by minimizing the modified action. So actually, in practice, what we do, we make a time discrete version of the scheme, and we put the residual in the formula, and we do the minimization. And in 1D, it turns out that you can do that by doing a lot of sorting algorithm. So it's very easy to code. Well, it's time consuming because you need a lot of iteration, but actually, you don't need to compute even the lazy gradients, because the time discrete version of the scheme handle that automatically in some sense. So that's a good advantage of thinking in a discrete way. So here, of course, there is a drawback to this strategy, because we are losing any kind of convexity for the action, and you may have a lot of minimizers. So, and this makes sense, because concentration, there is a loss of memory, and there is no reason that we should find a single solution. Yeah. So, but this is an example where we were able to reconstruct. So here we are not given the fluctuation at time 0. We are really taking a Zeldovich solution, and we assume that we already know the density at time 0.5. So. But I did some experiments where you can go up to 0, down to 0. So actually, this works. And you see that we have reconstructed a solution which is optimal for the modified action, but which would not be optimal for the original action. The original action, you would get all the rays will collide all together at the final time, which is absurd. So, but this way, with this kind of modified action, you can recover solutions that have concentrated before. And as a consistency, you can run the initial value problem back and see that the discrepancy. So actually, this was the evolution equation, and now I do the reconstruction, and I'm a little bit wrong here because I was not able to recover the collision at the right time. But here, this part is correct. So that's an example. And also to show you that you can get reconstructed solutions that are not for that's another situation where you don't expect the solution to be Zeldovich because you prescribe data at 0.5 and 2.5 that are not compatible with the first order dynamics. So you get some curvature like this of the curves. And this makes sense. And once again, here this is a case where you can reconstruct the trajectories knowing the final density and the initial density. And when you run the initial value problem, you get more or less the same. So the reconstructed velocity is fine to get the solution. So now let me finish. So the idea is among the minimizers of the modified action, we at least recover all the solutions of the gradient flow. So that take into account the concentration phenomenon. And the drawback of our approach is, of course, that we have cheated, except in 1D, with the model, because we have used the Mongeampere model instead of the Poisson model. And I don't know what to do with the original model involving the Poisson equation, I must say. So it works very well if we do this nonlinear modification of the model. And so I should say that, I mean, to do that numerically in higher dimension is much more challenging because you have to solve numerical optimal transportation in a higher dimension, which is not so easy to do. And so this is just some references if you are interested. So the discussion is more or less contained in these preprints. And so we have some reference on the EUR problem, Zeldovich. And this thing which was influential for me, this work of Gussoub about self-dual Lagrangian, because although I think it is not directly related, I think the idea of collecting the squares and to make it the square in the action of the first order dynamics was clearly a result of the discussion we had. And as a technical tool, we use optimal transportation. And that's it. So thank you for your attention.
Plenty of time.
Ah, okay. So I thought it was 2:30. Okay.
No.
Well, I mean, maybe there will be a.
You can continue.
Yeah. No, but I mean, it's over. So we can. Yeah. Ah, yeah, because we started at 45, right?
Yes.
Yeah. This makes the week lighter. So.
Okay. Is it okay?
Yeah.
Any questions? Next. You have time for
Yeah, you can think about the question first.
Yeah.
Thank you.
Just to know, would be a formulation of the Einstein equation in which you would replace whatever looks like a Laplacian in the Einstein equation by the Monge equation?
Well, yeah, that's not totally excluded because yeah, I mean it will need some work to check that. Because it's plausible that this formula is not worse than the Poisson equation, because the Poisson equation occurs when you are, this is from the Ricci curvature of the space-time, blah blah blah, and so usually you get, I mean, this in textbook you see the Laplace, the Newton gravitation popping up, because in the metric only the time coefficient plays a role in this approximation. But it might be that, because there is always this possibility of using different coordinates, that this formula could be okay, because this is like a Gaussian curvature, actually. This can be interpreted if you look at the function x squared over 2 plus t phi, and so this is like this and hypersurface, and this is the Gaussian curvature of the surface. So it's quite geometric. But it is, and I know that in some situation you can, the Ricci curvature doesn't look like the Gaussian curvature, but in 2D it's the same. I mean, you can relate them completely, but I think you have to play with the coordinates, and the worst thing is to play with the units, because to see whether the approximation is correct or not. But I know at least an example of a similar situation, which is the so-called semi-geostrophic equation. So this is more belonging to the other community visiting the Newton Institute at the moment, the people in meteorology and atmospheric science, because when you are looking at the Navier-Stokes equation with Coriolis force, and you consider a time scale where the Coriolis force becomes large, then you have a well-known approximation which is called a quasi-geostrophic equation. But if you play with the equation in a different way, essentially using Lagrangian coordinates instead of Eulerian coordinates, you get another approximation which is called semi-geostrophic equation. And in the 2D case, this more or less amounts to substitute the Monge-Ampère equation for the Poisson equation. And this comes from two different kinds of asymptotics. So this looks weird, but I think the discrepancy between the two models is small. I mean, you have it's like asymptotic equation. You know, it's not limits. So I think you neglect the same kind of terms. And the interesting feature is this semi-geostrophic equation were introduced precisely to describe frontogenesis, which is a one-dimensional phenomenon. So the shrinking of the situation on one dimension. And if you look at Zeldovic's theory, it's very similar because it's the theory of pancakes. So they explain that the gravitational instability will be dominating in the one dimension. So by, yeah. And the Monge-Ampère equation has a big difference with the Poisson equation. It has an affine invariance. So if you stretch the space, you don't change the equation. Of course, for the Poisson equation, it's not true. If you know, it's isotropic, but not affine invariant. So the Monge-Ampère is affine invariant, and probably this is what it is related to the asymptotics, where some direction can be privileged. And so maybe, yeah, but this should. But at the moment, I cannot claim that this is correct. Yeah.
Any other question? Yes. The Euler equation, the second order derivative,
Yeah.
times t time t.
Yeah.
So you said that at the beginning, this doesn't play any role.
Yeah, that's right.
No,
If you want bounded solution, because you have a very unstable mode, but which blows up at time t equal to 0. Either if you linearize the equation, this is what the cosmologists people did first.
No structure like initial layer or that kind.
I think if you look at time 0, the original equation, then you get this is really blowing up. Like, is it t to minus 1/3, something like that. So everything is unbounded. So this is the usual claim that if you want to make the analysis of the evolution, you should, I mean, this mode should be removed completely. And the other mode is slowly growing, and this gravitational instability is producing concentration. So according to the linear analysis.
Any other question? Okay. So if not, let's start.